Hello friends. Today I'd like to simplify the Lorentz transform equations for you. First of all, we need to understand what exactly is a transform. I would like you to observe this diagram in which we have two characters. One character is called Bibco. So Bibco is here and Chipco. So both these characters are actually observing a plane moving here. So let me show you the plane on top. It's moving in this direction. So this is the plane, and these two people are separated by 100 meter. Now observe that the x, y, z coordinates are shown here. These are the diagrams x, y and z. These two observers will observe this thing, the flying object. The y and z coordinates will be exactly same. However, the x coordinate, as observed by Bibco, the first guy, xb we'll call it, that will be equal to xc plus 100 meter, because there was a difference of 100 meter. The y coordinate is same, the z coordinate is same. Now, when they observe a certain event, first of all, what is an event? Event is something that can happen at a given space. At a given space and time. That we'll call it as an event. Now, the Lorentz transform actually transfers between, between two reference frames. One is a moving frame and the other with a constant velocity. So this transforms one form to the other, as we are about to see. There are two main transforms, I would call it. One is called as the Galilean transform, and the other is the Lorentz transform. So what is the main difference between the two? So Galilean transform, the Lorentz transform. The Galilean transform actually is valid only for all velocities much less than c, while as the Lorentz transform is valid for any speed. Here in the Galilean transform, time is universal, while as here time is relative. And you can also say that the Galilean transform converts to the Lorentz transform. In fact, Galilean transform is an approximation of the Lorentz transform when V is much less than C. So in the Galilean transform, what's going to happen is the x, y, z, suppose we have two coordinate systems, one here, which we'll call x, y, z, and the other one I will show in different color, which we'll call x prime, y prime, z prime, and this one is moving with a velocity v. Then the conversion is going to be something like this. X is equal to x prime plus v into t. The y and y prime will be same, z and z prime will be exactly same. Now that we have seen the difference between the Galilean and the Lorentz transform, let's derive the length contraction coefficient. I would like to consider two reference frames. So this reference frame which I am pointing here, they are actually two reference frames superimposed at this point. So at t is equal to t dash is equal to 0, you can see that both these are superimposed, but the red frame, so let's call, as per the previous case, the Bibco frame, which is a black one, and the Chipco frame, which is a red one. So this is Chipco So Chipko is here, Bibco is here. Just to note the difference. In the beginning, they were superimposed, but Chipko is moving with a velocity of v towards the right. And his frame of reference is x prime, y prime, and z prime. Now, we notice that x is equal to, let me show it here. Yeah, we notice that x is equal to gamma. Now gamma is what we want to derive. Gamma is called as the length contraction coefficient, and this is equal to x dash plus vt dash. Now notice that since it is a Lorentz transform, we have t dash. Had it been a Galilean transform, the t and t dash would have been the same. We also notice that in the second and third equation, the y and the z coordinates remain exactly same. So this is the equation we have. Let me highlight on it here. This is considered equation 1. X is the x coordinate of Bibco, that is equal to, that is a black frame, is equal to gamma, the length contraction coefficient, which is multiplied with x dash plus v into t dash, assuming that the red frame is going towards the right with a velocity v and experiencing a time t dash. So t dash is the time experienced by Chipko, the red frame. Now, let us consider from Chipko's reference point of view, Chipko's viewpoint, that is the red point. So from here, if you observe, what we would see is that the other frame is going towards the left with a velocity of v. So x dash, y dash and z dash, as per this observer, would be, x dash would be again gamma into x minus vt, minus because velocity is going in this direction. Of course, they would agree on the y coordinate and the z coordinate, which would be exactly same. Now, at t is equal to t dash is equal to 0, we notice that the frames are actually superimposed. So there is absolutely no difference of opinion. So let us assume at t is equal to t dash is equal to 0 that a photon of light leaves the origin and travels with a velocity of c. Now let us talk about frame F. Frame F is actually the Bibco frame, the black frame. So let me show that here. So this is frame F. So frame F, as you can see, frame F, x is equal to ct, frame F dash, that is F prime, this is the Chipko's viewpoint, x dash will be c into t dash. So this is equation 8. Now c into t, that is equal to x. This is from equation 7. But instead of x, I am substituting it from equation 1 as gamma into x dash plus v t dash, and that is, now the x dash is replaced as c t dash. So let me show it in a different color. Yeah. So you can see that this is ct dash. Now taking ct is equal to gamma t dash into c plus v. So this is going to be our equation 9. Now also note that from equation 8, ct dash is equal to x dash, but from equation 5, x dash is equal to, actually equation 4, sorry, this is equation 4, it is ct dash is equal to gamma into x minus vt. This comes from this equation. and x is replaced as ct, and that is coming from equation 7. Taking c common out from here, we got equation ct dash is equal to gamma into t into c minus v. Equating both, that is t dash is equal to, now take the c down, the c goes down, we get this gamma t into c minus v by c. Now let's replace the t as gamma into t. So this comes from the previous equation, gamma into t into c minus v by c into c plus v. Once we get that, that is this is substituted in equation 9, then c plus v into c minus v gives c square minus v square, and thus we get this equation gamma is equal to 1 upon square root of 1 minus v square by c square. Now notice that when v is much less than c, v by c will almost be equal to 0, thus giving us gamma is equal to 1. In other words, if you look at it, when you take gamma tending to 0, that is gamma tending to 1, the Lorentz transform actually tends to the Galilean transform. To finally summarize, let's see the consequences of the Lorentz transform. We have this equation here, L is equal to L naught into root 1 minus v square by c square. Here L naught is the length at rest, length of the meter scale at rest, and v is the speed with which it is moving. Now let us take, imagine an observer O is actually seeing this rod which is moving at a speed of 0.5 c. Now when it is at 0.5 c, you can see the calculation here which I have done. The length, substituting v as 0.5 c, we get the length as 0.87. So that means a 1 meter rod has actually become a 0.86 meter rod at 0.5 c. Now suppose we increase the speed to 0.75 c, that means 75% of the speed of light. The 1 meter rod now, as you can see, becomes 0.67 meter. So a rod of this size will appear to be a rod of this size. Now similarly, when experiments are done, say imagine that you are seeing a spacecraft which is actually, say, about 200 feet. So 200 feet spacecraft at rest would be 200 feet, but at 86.5% the speed of light, it would turn to be something like just 100 feet, half its size. And at 99% of the speed of light, it would just be around 28 feet. And at 99.99%, it would just be 3 feet. So the spacecraft would look something like this at 99.99% the speed of light. Also note that a typical circle shown here, as it moves, it will, with the speed closer to the speed of light, it would look like something like an ellipse. So these are some of the consequences of the Lorentz transform. I hope you enjoyed this lecture. I really enjoyed making this, and good luck to everybody. Thank you for watching.